Welcome back. Let's look at more practice questions under Math 1100. We now venture into mathematical induction. Question number 1. Prove that for every positive integer n, 1 cubed plus 2 cubed plus 3 cubed plus dot 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 plus n cubed gives us n squared open brackets n plus 1 squared over 4. So we always start with a base case, which is in step 1. Okay, so you assume the statement, not assume, prove. All right, prove that the statement is true, all right, for n equal to 1. So where there's n here on my left hand side, my left hand side has got one n there, okay, is n cubed. So I'm going to put 1 there to just give me what? 1. I'll also prove my right hand side if I'm getting the same. My right hand side is n squared, n plus 1 squared over 4. So if I put 1 here, this becomes that squared. This is 2 squared, which is 4 over 4, and I get 1. And you can see from here to say my right hand side and my left hand side are what? Are equal. Therefore, the statement is true. Isn't it? With step 2, okay, we need to prove that. Here we don't prove, but we assume. It's an assumption. Assume that the statement is true for n equal to k. What is statement? So we copy the entire statement. Okay. Okay. So where there is n, you put k. You put k squared, then k plus 1 squared over 4. You end it there. Step 3, prove the statement is true for n equal to k plus 1. Okay. Step 2 is also known as the inductive step, while step 1 is also known as the base case step. So here, what we are going to do is that get the entire part of statement 2. Okay. So all what we are doing is get statement 2 and just from the left hand side, just add this. Do this. So you say this, then you add k plus 1, then you cube like that. So here you get k plus 1 square. Now where there's k, I'm going to put k plus 1, but there's already another k plus 1. So there's another 1 there, which will give me k plus 2 squared over 4, like that. Now you can see that this part here is actually coming from step 2. The whole part here is step 2. So since this part is step 2 and step 2 is equal to this, get that same term there. Where do I like x? Over 4. Then you say plus k. You see? This is equal to k plus 1, k plus 2 squared. These two should be equal actually. Okay? They should be equal. Here should be k. So when you expand this side and this side, the question is, are they going to be equal? Yes, they are going to be equal. Okay? They will be equal. And it's our job to prove that. Okay? So let's do. So common denominator is what? 4. Okay? So here I'll just get k squared. There's 1 here, so 4 multiply here. Why do you like x? Sure. Cube like that. Let's keep this one the way it is. Okay. So you can expand here. Of course, here there is squared. So I've got k squared. If I expand here, I'm getting k plus 2k plus 1. Then I'll say plus, what about expanding this one? Okay, let's do this. Expansion may look too long. Let's just factorize. There's k plus 1 squared and k plus 1 cubed here. So k plus 1 squared is common. So we can just say k plus 1 squared is common. Okay. So if I factorize it here, I'll remain with what? K. And what am I going to remain with here? 4k plus 1. Over 4. Is this equal to k, then k plus 2 over 4? Are they equal? Yes, they are. When you try to square this part here, you'll be getting a 4 somewhere. And that's a 4 coming out from here. Clearly, right? Because this part is this part. The entire part here, this entire part here, is just this. Try to square this. You start, you're getting the same thing as here. So the left hand side equals the right hand side. Okay? Therefore, we can say the statement 1 cubed, 2 cubed, this one is true for all positive integers what? N. That's all.